All right, so today we're doing Chapter 8, Section 3, Rational Functions and Their Graphs. Our learning objectives are to identify properties of rational functions and to graph rational functions. So essential understanding is, if a function has a polynomial in its denominator, its graph has a gap at each zero of the polynomial. The gap could be a 1-point hole in the graph, or it could be the location of the vertical asymptote. So let's go ahead and highlight those pieces here. We're going to highlight gap, we're going to highlight 1-point hole, and we're going to highlight vertical asymptote. A rational function is a function that you can write in the form of f of x equals p of x over q of x. So there's your polynomial in the denominator, where p of x and q of x are polynomial functions. The domain, and you guys will get a ton of questions about domain and range. So the domain of f of x is all real numbers except for those values where q of x, or your denominator, is 0, because the denominator is not allowed to be equal to 0. So let's take a peek at the three different scenarios. I like this one because it looks like a little book. Y equals x squared over x squared plus 1. It makes this little book shape. This is where it has like a sharp point here at 0, 0. This guy here is a situation where we have our denominator equals x plus 2. So we're going to have a hole where that denominator equals 0. So it's got this little hole right there at x equals negative 2. And then this guy right here, he has got x minus 2 in the denominator, but the way he's situated, it's at x equals 2, we have a vertical asymptote. And usually a vertical asymptote, if you guys are graphing it, is depicted by a dashed line. Okay, so those are a couple of scenarios. Make sure. For the first rational function, y equals x squared over x squared plus 1, there is no value of x that makes the denominator 0. Because if I square anything, I'm not going to get negative 1. So there's no real number that makes the denominator 0. The graph is a continuous graph because it has no jumps, breaks, or holes. And that's the definition of continuous graph. Has no jumps, breaks, or holes. You can draw the graph and your pencil never leaves the paper. For the second rational function, y equals x plus 3 times x plus 2 over x plus 2, x cannot be negative 2. For y equals x plus 4 over x minus 2, x cannot be 2. The second and third graphs are discontinuous graphs. And discontinuous graphs have jumps, breaks, yep. All right, key concept. Point of discontinuity. If a is a real number for which the denominator of the rational function is 0, so let's highlight the important words here. Denominator is 0. Then a is not in the domain. The graph of f of x is not continuous at x equals a, and the function has a point of discontinuity at x equals a. The graph of y equals x plus 3 times x plus 2 over x plus 2 has a removable discontinuity at x equals negative 2. The hole in the graph is called a removable discontinuity because you can make the function continuous by redefining it at x equals -2, so that f of -2 is equal to 1. So you can be a sneaky ninja and add a different piece to your function to make it a piecewise function and remove the discontinuity. The graph of y equals x plus 2 over x plus 4 over x minus 2 has a non-removable discontinuity at x equals 2. There is no way to redefine the function at 2 to make the function continuous. When you're looking for discontinuity, it is helpful to factor the numerator, that's the important part, and denominator as the first step. The factors of the denominator will reveal the points of discontinuity. The discontinuity caused by x minus a to the n in the denominator is removable if the numerator also has the x minus a to the n as a factor. So if you can factor out, you guys look here, it's this x plus 2 and x plus 2. If you can factor that out, then it is a removable discontinuity. All right, now that we have all this information, let's go ahead and apply it to some math problems. Yay! What are the domain and points of discontinuity of the rational function? Are the points of discontinuity removable or non-removable? What are the x and y intercepts of the rational function? All right, so if we take a look, we want to make sure the first step that they suggest for us to do is to factor the numerator and denominator, so we're going to go ahead and do that. So if I have 1 in the numerator, I can't factor that. But if I take the denominator here, x squared minus 16 is the difference of squares. So that can be factored to x minus 4 and x plus 4. We don't have anything canceling out on the top, so it is not a removable point of discontinuity. We just say that x equals 4 and x equals -4 are not our points of discontinuity. So these are points of discontinuity. Lots of fun vowels in there. And it is non-removable because the numerator does not cancel. It's non-removable. And what are the x and y intercepts of the rational function? This is a fun question that is we did kind of like in the earlier chapters, so I don't blame you if your mind just is completely blank. The x-intercept is when y equals 0, and the y-intercept is when x equals 0. So we're going to plug in 0 for x to find the y-intercept. And we get y equals -1/16. So the y-intercept is at 0, -1/16. Be careful with these. When you go to input them into your quiz, it may want it in fraction form. So if you use a graphing calculator or graphing utility to find it, you're going to have to be aware of how they're asking you to submit it. And then x equals 0, when y equals 0, is there an x value where y is equal to 0? Can I have any x value where y is 0? So we look at this statement here and we say, we're not going to have a y-intercept. There is no y-intercept because there is no x value that we can plug in and get a true statement for 0 equals 1 over x squared minus 16. So let's put this, here are the points of discontinuity. Here is the y-intercept. There is no x-intercept. And now we are only missing the domain. So the domain is all real numbers. Except x equals plus and minus 4. All right, I'm going to do C here with you guys. The very first thing it says that we should do is factor the numerator and the denominator. I look at my denominator because my numerator is already factored. He's got nothing we can do with him. And I say, what two numbers multiply to give me 2 and add to give me 3? That would be 2 and 1. So if we look at domain, and domain is when the denominator is all real numbers except when the denominator equals 0. So our domain is all reals except x equals -2 and x equals -1, because those two values will make the denominator 0. Do I have a factor that can cancel out? Okay, so I have, here's a funny trick. This one and this one, those two factors will cancel each other out. So I have a removable I didn't stick with my original trick where I just write really messy so you can't tell that I am misspelling things. Removable discontinuity at x equals -1. And I have a discontinuity it's a non-remover at x equals -2. Because this guy didn't cancel, so we're unfortunately stuck with him. What are the x and y intercepts of the rational function? This will be fun. So I can't, if I plug in 0 for x, let's get the y-intercept. If I plug in 0 for x, I get 0 plus 1 over 0 squared plus 3 times 0 plus 2. All the 0 shenanigans go away and I get 1/2. So I have a y-intercept at 0, 1/2. And is there any place that's going to get me out this guy equal to 0? Is there anything I can put in here where this guy is going to equal 0? So if I put in -1, I get 0 at the top, but my denominator explodes. I could put in -2, but that only makes my denominator explode. Because 0 times anything is going to be 0. So I'm going to have no x-intercept. It's okay to have to think about that for a minute. All right, vertical asymptotes. The graph of the rational function, f of x equals q of x over q of x, has a vertical asymptote. So let's highlight the important stuff out of here. We got a vertical asymptote. Remember, vertical is up and down. At each real zero of q, as long as p and q have no common zeros. If p and q have a common factor and m is less than n, so this is kind of important too. If p and q have x minus a to the m and x minus a to the n as factors, and m is less than n, then f of x also has a vertical asymptote at whatever that a value is. So let's take a peek at some examples of that. What are the vertical asymptotes for the graph of the rational function? Y equals x minus 2 over x minus 1 times x plus 3. So a vertical asymptote happens when your denominator equals 0. That is at x equals 1 and x equals negative 3. All right, so x equals 1 and x equals negative 3. There is not a similar factor that cancels out between the two. So these are the vertical asymptotes. X equals 1 is a vertical line at 1 over on the x-axis, and x equals negative 3 is a vertical line over at negative 3 on the x-axis. All right, so let's take a look at B. Ask what the vertical asymptotes for the graph of the rational function. We definitely have one at x equals negative 3 because I got nothing that cancels out. It's not the same factor on the top and the bottom. But let's take a look at these ones. X minus 2 has a power of 1. The one on the bottom also has a power of 1. The rule up here says my power on the bottom needs to be bigger than the power on the top. I'm just looking to see if it specifies. Respectively. So P has the M, Q has the N. So my power in on the top has to be less than the power on the bottom. We do not have that scenario. So x equals negative 3 is our only vertical asymptote. X equals 2 is a whole. When you get a factor that cancels and goes away, then you have a whole. All right, let's take a look at our last one. We have x squared minus 1 is the difference of squares. So we go x minus 1 and x plus 1 is what it factors. And then we got x plus 1 in the denominator. I have only in my denominator the factor of both the top and the bottom, x plus 1. They have the same degree. When you have the same degree and it cancels out altogether, it is not a vertical asymptote. It is a whole, so there are no vertical asymptotes. All this talk of vertical asymptotes, what about the horizontal ones? Side to sidesies. Where are those? Well, the graph of a rational function can have any number of vertical asymptotes. It can have no more than one horizontal asymptote. Thank goodness, because that sounds like more work if we get more than just one horizontal asymptote. We can only have one horizontal asymptote. Okay, so let's figure out if we got one or none. So to find the horizontal asymptote of the graph, compare the degree of the numerator to the degree of the denominator. Find the highest degree, and that's all multiplied out. So if the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is at y equals 0. So if the top has a lower degree than the bottom, you're going to always get y equals 0 as your horizontal asymptote. If the top degree is larger than the bottom, there is no horizontal asymptote. And if they are the same, then your horizontal asymptote is at the coefficient of your highest degree on the top over the coefficient of your highest degree on the bottom. So let's see how that plays out here. So we're going to do a little test for the horizontal asymptote. So y equals negative 2x plus 6 over x minus 5. The highest degree of the numerator is 1, and the highest degree in the denominator is 1. They both have the same degree. Now we're in this scenario. What is the coefficient of my highest degree term on the top? It is negative 2. What is my coefficient of the highest degree on the bottom? Let's see if you guys can think of it. And then simplify it, so y equals negative 2 is my one and only horizontal asymptote. Asymptotes are complete lines. So you better have an x. If you're talking horizontal asymptote, you better have a y equals attached to it. If you input just the number, you're not answering the question correctly. All right, so for B, let's go ahead and factor our little friend. Actually, I'm not going to factor it. We're just looking for horizontal asymptotes. So we got, so we have degree. This term here is our highest degree term on the top. His degree is 1. This guy here is the highest degree term on the bottom. His degree is 2. So when the top is less than the bottom, we have a horizontal asymptote at y equals 0. Yay! Done. How fun is that? Okay. This scenario. This scenario, we have degree 2 on the top and degree 1 on the bottom. When the degree on the top is greater than the degree on the bottom, there is no horizontal asymptote. I'm going to abbreviate that with I. All right, so now we're to the purpose. Why bother finding horizontal and vertical asymptotes? Because it helps us get a reasonable graph for our rational functions by finding all intercepts and asymptotes. Sometimes you'll have to plot a few extra points to get a good sense for what the graph is going to look like. So remember how we can't have a calculator on our final, and you can't have Desmos or a graphing utility on your final. So when you're asked to graph a rational function, you've got to know where all the asymptotes are, know if the graph is above or below, and its general shape. So we're using all these pieces of information to help us with that. Okay, so let's do a problem here. That's not the one I wanted. Am I not? This is fun. So we're going to graph y equals x squared plus x minus 12 divided by x squared minus 4. We look for the horizontal asymptote, the same degree polynomial. So we get 1 over 1 because the coefficient of each of our x squared terms is 1. So we get a horizontal asymptote at y equals 1. And as you get each of these pieces of information, you can start putting a picture together. So at y equals 1, we have a horizontal asymptote. We're going to factor the numerator and the denominator, and then we can identify any holes or discontinuities or vertical asymptotes. So we get x plus 4 times x minus 3 over x plus 2 times x minus 2. That leaves us with a vertical, because nothing cancels out, it leaves us with the vertical asymptotes at x equals -2 and x equals 2. So I know no matter what happens on this graph, I'm not going to touch those asymptotes. When the numerator equals 0, y equals 0. So that is at -4, comma 0. Put that in red. So right here. And at 3, comma 0. That is right here. So my graph crosses. It can't get any bigger than here, and it crosses the x-axis here, and it can't get any closer than this point right here. Same thing with this guy over here. I cross right here, but I'm only restricted. I can only go one way and then the other. I can't. Those asymptotes really bind me into not being able to move. So when I plug in 0 for x, I actually have a y-intercept this time. I'm also going to pick him. So we put in 0, we get 4 times -3 over 2 times -2, which gives us 3. So our y-intercept is at 0, comma 3. So it's up here. So the only direction I can go to the right of that intercept is that way, and the only direction I can go to the left is that way. I got no, although I guess I could use the square function. -1, 4. So you pick a couple of other points on your graph to kind of make sure your shape is going in the right direction. So if we plug in -3, you get -6/5, which is like 1.2. That's like over -1.2, so that's over here. When I plug in -1, I get 4, which is right around here. When I plug in 1, I get 10/3, which is like over here. And when I plug in 4, I get 2/3, which is positive. So that gives the rest of the shape of that graph. And that's the reason we do asymptotes in the first place, is to give the shape of our graph. All right, so let's look at this hard problem. You want to mix 10% orange drink with 100% pure orange juice to make 40% orange juice drink. Thankfully, we have a function that will calculate that for us. Y equals 2 times 1.0. 1.0 is the 100%, plus x times 0.1. 0.1 is the 10%, divided by 2 plus x. Gives the concentration Y of orange juice in the drink after you add x gallons of the 10% drink to 2 gallons of pure juice. So this 2 is the 2 gallons, just in case you want to use this as your portfolio question. 2 is the 2 gallons, 1.0 is the 100% here. X is the amount you're adding, 0.10 is the 10%, And then 2 gallons is this 2 still here? 2 gallons, 2 gallons. And so how much of the 10% drink must you add to get a drink that is 40% juice? So there's 2 options here. We can either go 40 or we can go 0.4. So I want my concentration, and which one do you think it's going to be, 40 or 0.4? So because they used 100 as 1.0 and 10 as 0.1, we're going to use 0.4 to represent the 40%. So we're going to solve this. I'm going to solve it actually by graphing. All right, so I'm going to set y equals to 0.4 to the what's on the left-hand side of the equation, and then y equals our function. And I get that I need to add 4 gallons in order to get a concentration of 0.4. Actually, let's add that to, go ahead and sketch the picture in your notes so that it makes sense where things are coming from and that you just didn't make it up out of thin air. It's called evidence. You got to back up each of your answers with evidence, a reason. So because of this graph, we can say that the concentration of 40% needs 4 gallons of 10% added. Okay, take a moment and write your summary. Make sure you include the learning objectives, and we had a bunch of essential understanding, bunch of information about vertical and horizontal asymptotes.